Hi guys, hope you're well. Right, let's get straight on. Now, before we start today's lesson, I just want to please, if you can, start uploading. I know some of you are already. Please do upload your stuff onto the OneNote page rather than emailing me the work. It's much easier for me to keep track of, and I can also mark the work there. So I'm just going to. It's the Further Maths page. I think you've all probably got access to it now. So I'm just going to show you what we can do. So I think Amelia did this last lesson. So if we go, she's put it in her homework there, her iteration, and it's all there nice and neat, and her dates up there, which is good. And I can mark it and I can say, very good work, which it is. Okay, so please do use this. Now, it's the best way to upload onto OneNote. I mean, Amelia's used CamScanner, which is I'd really recommend. There are two ways of doing it. If you've got pictures, just go pictures there, and you can either do it from a file, or if you're using an iPad, straight from the camera of the iPad, take a picture. It goes straight into this page. That's really good. If you've got a PDF, like Amelia did, you go to Print Out, and you find the folder there. And you just open it and it comes up really nice and neat. So please use this rather than emailing me. Now, there is a few of you here, Ben, for example, who I haven't received any work for so far. So Ben, if you're listening out there, it isn't going unnoticed. And if you don't get me work soon, your parents will be receiving an email, which I'm sure they can do without. Okay, so that's just a bit of a start. Remember, all the lessons are going to be, all the work to the lessons is going to be in here. Okay, so you can access that as well as going back onto the video as well. You've obviously got the video, but you've got all the notes in here from the previous lesson. So that's where we're going to put them. Right, okay, I'm going to disappear now, and we're going to start with a starter activity. I'm going to give you 10 minutes to have a go at this. Okay, really important. I want to see this as well when you send in your working. So you've got 10 minutes. Off you go. Okay, that's about time, guys. Please can you mark your own work? Here we go. This question 1, you needed to differentiate it, and then you sort of solve it when it's equal to 0. Again, here we've got an integral here. Don't forget the plus c, 6 seconds. And this one here, the lines are not parallel because the gradients are different. And they're also not perpendicular because when you times the two together, you do not get -1 as an answer there. So that was what we did there. Okay, right. Can you get your books out now? Well, books should have been open already, but put a new title back to the front of your books. And we're carrying on with numerical methods. The date is the 26th today, I think, and the Newton-Raphson method. Okay, Newton-Raphson method. Now, this is a way of solving, again, it's an advanced trial and error, really, to home in on the solution. It's a little bit like what we did last time. It was sort of invented by this guy. I mean, Newton pretty much invents everything, but he invented it. Raphson developed it and made simple to use, I suppose. So yeah, he did enough to be recognised to get his name on the title, but Newton's the main man here, like he seems to always be. Okay. Now the beauty of this method, it is much faster. It's much faster than iteration, which is really, really important because most computers use numerical methods to solve solutions, and the faster you can do it, the quicker a computer can program it, and that's worth a lot of money in the real world. So the quicker you can do things, or the quicker your computer can, that's really, really important. And it solves solutions. It solves solutions. Okay, there are some problems with it, which we'll talk about at the end of the session. But that's what it's there to do, and it can do something like this. So we're gonna build it from solving. So we're going to solve using the Newton-Raphson method, x cubed plus 2x minus 2 equals 0. Okay. Now to start with, it must be in the form fx equals 0. Okay, so in order to solve something, it has to be equal to 0. Sometimes you may need to rearrange. Into this form. Okay, you may need to arrange into this form. I mean, this question is already in the form already, so we're just going to solve this cubic. Okay. There are ways of solving. We could use the formula, couldn't we? We could use our calculator to do it, or we could use iteration, but we're going to use this Newton-Raphson method today. Now, if I was to sketch this curve, okay, now it's cute. I'm going to zoom out. I'm going to stretch it a little bit because it's going to help. It will look a bit like this part of the curve, but it's a cubic. Okay, now this is y equals x cubed plus 2x minus 2, and we're solving the solution. We're solving when it equals 0, so we're trying to get that point. That is what we're trying to achieve. We're trying to achieve that point there. Okay, now I know that point, and it's a bit of I know it lies somewhere between 0 and 1. Okay, now this method, like the last method, it relies on you to have a first guess, which is one of the negatives of all these methods. But it does rely on you to have a first guess, so you need to almost roughly know the answer. And I'm going to call my first guess 1, because I know just from experience that that's going to work for this question. Again, a little bit like iteration, if you pick the wrong starting point, it can either be very, very slow, or it can not converge at all. So I'm going to pick 1. Now what I do here is I come up at 1 and I find that point. Now at that point I draw the tangent to the curve at that point. Okay, I'm going to do it in a different colour. So I draw the tangent to the curve at that point there. See, it's going to look something like that. Okay. Then what I do is my next input will be there. x1. That will be my next input. So I need to work out what that will be, and so on. Then I go up again. Once I've got that input, I go up to the curve, and again, I'll do a slightly different colour this time. I then draw the tangent at that point, okay, and you can see very quickly now, that would be my second value, and you can probably go up, and then I go so on, and you can see that it very quickly, much quicker than iteration, zooms in on that solution. Okay, it zooms in on that solution really, really fast. In fact, sort of a magnitude of double. So it's twice as quick as the iterative methods, which is why it's so powerful. Okay, right, let's actually do this problem from first principles, and you'll see how the form. I don't just want to tell you the formula. I want you to be able to build it from scratch. I think you could probably do it yourself, but let's see what we do. So what I need to do, let's look at the blue line first. So the blue line. Now, I know to work out the equation of the blue line, I'm going to need to differentiate first. So I'm going to say, okay, y equals x cubed plus 2x. Is it 2x? Yeah, minus 2. So dy dx. In fact, I'm going to start using the notation that's in the formula. Fx and f dash x is 2x plus 2. Okay, so the differential of that is 2x plus 2. I know my starting value is 1. Now so I know that's my starting value. So at x equals 1, f dash x of 1, the gradient function, sorry, that should be, so the gradient function will be 4 there. Okay. Sorry, apologies. This is live. I've differentiated that equation wrong, haven't I? It's 3x squared. Oh, I need you guys to spot the errors. Glad I didn't go any further with that. Right, okay, so f dash 1 is going to equal 5. Okay, so the gradient of that blue line is 5, which looks about right. So I know it's y equals 5x plus c. Now I need to work out a coordinate. So I need to work out that coordinate really. So over here, a bit of side working. So when x is 1, y is going to be 1 cubed plus 2 times 1 minus 2, and that also turns out to be 1. So f1 is equal to 1. So I've got a coordinate. I know this line passes through the point 1, 1. X is 1 and y is also 1. So 1 equals 5 times 1 plus c. I know my c is going to be minus 4. So the equation of the blue line is going to be y equals 5x minus 4. Okay, that's the equation of the blue line. So let's put that up there. Let's put it in blue. Y equals 5x minus 4. Right, what I need to find out is this point. I need to find where it crosses the x-axis. So when y equals 0, 0 equals 5x minus 4. 5x will equal 4, so x equals 4 over 5, or 0.8. So I know my next input here is going to be 0.8. 0.8. So then I'm going to go up, and the problem here is I'm going to have to do the whole process again. I mean, it's slightly quicker because I've already differentiated it there, but I'm going to have to put in all the values again, and then I'll get a new value and it's going to be this value here, and I'm going to have to do it all again. But is there a way, this is why it's a sort of, you can see it's a repetitive method, a bit like the iteration method. So let's try and build the iterative formula from what we've just learned, okay? Right, so now I know that 0, if I go, it's always going to be equal to 0. These equations of lines, I'm always going to set them equal to 0 because I always want to know where they cross the x-axis. So y is always going to be 0. Now that 5 here is the differential, isn't it, of x. Now in this case it's f, it's the differential, and it was x0. That was our first x value, wasn't it? So that there is the equivalent of the 5 bit. X goes in, okay, x. Now that was our following x, wasn't it? That was our next value of x. That was our next x value. next x value. Okay, that's our x bit. And then we've got plus c. Okay, so we've got plus c. We need to work out what the c is. Now the c, if you think about it, so c, if we go up here, let's look at what c actually was. Now that left-hand side there, well, that was just f of 1, wasn't it? Or f of x naught. So f of x naught. Now the 5, again, that's the same. That's f dash of x naught. And the 1 there, well, that was x naught itself. So x naught plus c. Okay, so if we rearrange that equation, c equals f x naught minus f dash x naught. All multiplied by x naught. Okay. Right, let's stick that down into here. So I'm going to replace the c this time with what we've just worked out, which was f x naught minus f dash x naught. So please do pause it. This bit's quite tricky to get your head around. Times x naught. Okay. Right, now at this point, I can now divide through by f dash x naught. Now if I divide every term by this, I end up with 0 divided by anything is 0. That's just going to be x1. This is going to be f of x naught over f dash of x naught. And this is going to be minus, because the f naught, they're going to cancel out, minus x naught. Okay. Right, so my x1, my following x value is going to equal x, my previous x value, minus f x naught over f dash x naught. And that there, all they do in the formula is they just put xn plus 1. The following x value is equal to the previous x value, xn, minus the f of the x value over the differential of the previous x value. That's the formula you'll see in the formula book. That's the formula you need to learn. I think it's really good practice if you can try and follow the steps to see where that's come from, because it's really important that if you know where it's come from, you'll understand it a lot better. That's the formula that's really, really important. Okay, and just in practice, we'll use this example to show you how you can use it quite quickly. So you need to start by, okay, fx equals x cubed plus 2x minus 2. I need to be able to do that. I need to be able to differentiate it. 3x squared plus 2. Okay, now this is one of the problems. So this is one potential problem. I can see some of you already noting this probably. You must be able to differentiate. If you can't differentiate the function, then this method just doesn't work, because, well, you need to be able to differentiate it, and in reality a lot of functions can't be differentiated that easily. So in reality it's not as used as it might be, but for this case it can be differentiated, which is nice. So then I can go straight in. I also need a starting value, and again the starting value is really important. If I pick the wrong one, I'm going to get an answer that goes further and further away from the solution, or one that may not work, or it'll be really, really slow. And for this particular example, I'm going to use 1. The other thing you've got to note is if f dash x equals 0 at any point, the whole thing breaks down, because again it breaks down because you can't divide by 0. Okay, that would be 0, which would break the rules of maths. You can't divide by 0. So if f of x is ever equal to 0, which is why it struggles for stationary points. So don't start when it could equal 0 like that. Okay, right, let's run this iteration now. So x0 equals 1. My next value is going to simply be my previous one, which was 1 minus f of 1 over f dash of 1, and in this case we know that equals 0.8, and then I just put that into the next one. Now in reality, just put this into your calculator. They use the answer key, so it's the answer key, answer cubed plus 2 times the answer minus 2 over 3 answer squared plus 2. And if you keep pressing equals on that, you end up homing in on the answer so fast, but it's about 0.77 is the solution, and that is how you work out the solution of using the Newton-Raphson method. Okay guys, what I want you to do now is to please go to page 284, and I want you to do questions 1 to 7 inclusive, so the whole exercise please, and as an extension, can you try the challenge question? Okay, try the challenge question as an extension. Please upload work to OneNote, and there's a few of you, Ben, who haven't uploaded anything yet, so please, I'm going to be chasing you on this, and please, if you've got Ben's number, give him a bit of a hard time, make sure he submits the work please. Okay, thanks guys, I'll speak to you again tomorrow. Stay safe.